In the last lecture, we discussed about the fundamentals of the transistor, basic transistor circuit, how to bias the transistor, and what are the characteristics of the transistor and what is load line. Okay, so today we will see how we can check whether the transistor is in a particular mode of operation. Okay, so we will see how we can check it, whether it is in a active mode, whether it is in saturation mode, whether it is in cutoff mode. Okay, so in cutoff mode, you know that both end will be reverse biased and there won't be any current through the transistor. And in saturation mode, the current will be the transistor will be forward bias, so the current through the transistor will be determined by the other components. Okay, like the resistor in series, and the transistor will lose all its properties. In active mode, the resistor will not play any role in determining the current. Actually, if the transistor is in active mode, the current will be completely the collector current. I'm talking about the collector current. The collector current will be completely determined by the base current. Okay, because IC is equal to beta DC times IP. So I want to just remind you that in cutoff mode, actually no current. In active mode, okay, the current IC is equal to beta DC times IB. Okay, and in saturation mode, what will be the current? In saturation mode, the current IC will be determined by other components in the circuit. Okay. Other components in the circuit. Okay, that is very, very important. So now we will see how we can we will see a problem. So the problem is determine whether the transistor in the circuit below is in saturation or not. Okay, assume VCE at saturation is equal to 0.2 volt. Okay, so a circuit is given. So I will draw the circuit. So you have a transistor circuit which is having RB, VBB, and this is grounded, and you have something RC here and VCC. Okay, VCC. So this is what the circuit, and RC is given as 1 kilo ohm and VCC is given as 10 volt. Okay, and RB is given as 10 kilo ohm. Okay, and VBB is given as 3 volt. Okay, VBB is given as 3 volt. We want to check whether this transistor is in saturation or not in saturation. This is what the main part of the question. So in saturation mode, you know that the current in saturation mode, so before writing the answer, in saturation mode I told you the current will be determined by the other components. So in saturation mode, IC will not be equal to beta DC times IB. Okay, the transistor will lose all its properties. Okay, that is the main idea that we have to care about. Now you see here, we will see what is the current if beta DC is also given. Anyway, beta DC is equal to 50. So what will be the current if we are applying our normal formula like IC is equal to beta DC? Okay, now you know that if we write the Kirchhoff law, in loop 1, okay, so in loop 1 if we write the Kirchhoff law, you know that this is minus, this is plus, the current IB will be going inside, so this is plus and this is minus, and you know this voltage VBE is 0.7 volt. Okay, So in loop 1, if I write the Kirchhoff law, KVL, you can see here minus VBB, okay, then you can see this is plus and this is minus, so minus VBB, then plus IB into RB, okay, and then plus 0.7, okay, volt, that is 0.7 volt is equal to 0. So what is IB? IB is equal to VBB minus 0.7 divided by RB. So you will get this as 3 minus 0.7 divided by 10 kilo ohm, okay. So you will be getting this as 0.23 milliampere, okay. Now you can use this, you can use our idea that by assuming in active mode, okay, this is by assumption, by assuming in active mode, okay, we are calculating the current, okay. Now we have got IB as 0.23 milliampere, okay, that's it. Now we are going to find what will be the IC by assuming in active mode, okay. This is just an assumption. If our assumption is wrong, we will get something else. We will see how we can assume something like active mode and calculate and find whether the transistor is in saturation or not. So by assuming the transistor is in saturation mode, okay, is in active mode, active mode. So IC is equal to, so this is by assumption, so IC is equal to beta DC times IB. This is the situation in active mode. So beta DC is 50 and the current IB is 0.23 milliampere. So the current is 11.5 milliampere, okay. So we got the current according to this assumption. According to the assumption, we got the current like 11.5 milliampere. Now we will assume, by assuming, so this part is over, okay. Now by assuming the transistor is in cutoff mode, sorry, not cutoff mode, saturation mode, since the transistor is in has some current, this clearly indicates that it is not in cutoff mode, okay. This is also giving you an idea that it is not in cutoff mode, okay. It is not in cutoff mode because there is some current through the transistor. But what about this? What is the situation of this current? Whether IC is equal to beta IB is valid or not, whether it is a true current, that we are going to examine, okay. So by assuming the transistor is in saturation mode, we can write, we have this circuit like this, okay. We have RC and VCC, okay, that's, now we have something like RB and VBB, okay. Oh, this is connected here, okay. So this is the situation, okay, everything is grounded. Now we will see this voltage is VCE, and assuming the transistor is in saturation mode, you know that VCE sat is given in the question, because in the question VCE sat is given, you can see here VCE sat is given as 0.2 volt, okay. So if the transistor is in saturation, the voltage across the collector and the emitter, that means VCE between the collector and the emitter, is 0.2 volt. So with this assumption, we will write the Kirchhoff law again. We will write the Kirchhoff law in this loop. So this is loop 2. So for loop 2, we will write the Kirchhoff law, KVL. So with this assumption, by assumption is, my assumption is like this. So this is starting from here, this is minus, this is plus, so this is minus VCC. Then if the current will be going like this, so if the current moves like this, this is plus and minus. So again this is plus IC into RC. Then the current is going down, so this is plus and this is minus. So the polarity will be plus VCE is equal to 0. So what is IC? I can write IC is equal to, so I am talking about the saturation mode, because you see here, by assuming in the saturation mode. So in saturation mode, my current will be IC sat and my voltage VCE will be VCE sat. Okay, so I can find my IC sat into RC as VCC. I can rearrange this equation, VCC minus VCE sat. Okay, so what is my IC sat? IC sat is equal to VCC minus VCE sat divided by RC. So I am going to find this current. So we know that VCC has been given in the question. VCC is given in the question as 10 volt. So 10 minus VCE sat is 0.2 and RC is given as 1 kilo ohm, which is equal to 9.8 milliampere. So we got IC sat as 9.8 milliampere. So my actual current IC sat, not actual current, IC sat is 9.8 milliampere, and I have got previously with this assumption I have got something like my IC. So this is in the case for saturation. Okay, and I have got something like IC is equal to, by assumption in active mode, by assuming the active mode, I got my IC as 11.5 milliampere, right? So this is by assuming active mode. So you can see here, I have a current which is much greater than the current which is required for saturation. So this current you can assume, is the current required, you can consider this as the current required for saturation. You need only 9.8 milliampere for saturation, but the current that can be provided by the relation IC is equal to beta IB is nothing but, our IC is nothing but 11.5 milliampere and our IC sat is 9.8. So you need only 9.8 and your IC actually according to the transistor relation, it can provide actually 11.5 milliampere according to the circuit configuration. So for example, if you have a pass mark of 60 and you have got 70, that means you are passed. So you can see here IC sat is greater than IC, that means not IC sat, IC, your IC is greater than IC sat. That means that your transistor is moved to has moved to the saturation mode. So the transistor is in saturation. So the transistor is in saturation. So let me ask you, the transistor is in saturation. So what will be the actual current through the transistor? That is the main part of the question. So the transistor, so actual current, since the transistor is in saturation, the actual current will be 9.8. Whenever the transistor reaches the saturation, actual current will be only 9.8. It will not be actually 11.5. It is because 11.5 is, you are getting 11.5 by using the transistor relation. That means IC is equal to beta DC times IB. And this equation will not be valid in saturation mode. Whenever the transistor reaches the current 9.8 here for this circuit, then IC will not be equal to beta DC times IB. Now you can change the current by changing the circuit configuration. That's what you see here. This is RC and this is VCC, and we have seen that this current IC sat is equal to 9.8 milliampere. Okay, and we have RB and VBB. What you can see is that once the transistor reaches this current 9.8, whenever it reaches the current 9.8, it cannot be further increased. Okay, because whenever it reaches the saturation, in saturation, IC is no longer equal to beta DC times IB. So the current will change. So if you change in saturation, if you change the RC, what will happen? The current will change. IC will change. Okay, this is the situation in saturation. But if the transistor current is, so this is the situation. If IC is less than IC sat, then the transistor is in active mode, you can say, in active mode. If, this is only if, okay, but in our problem it is not satisfying anyway. So if IC is less than IC set, the transistor will be in active mode. Then you can calculate IC as beta DC times IB. So in that case, if you change RC, then IC will not change, because IC is depending only on beta DC times IB. So this is the situation in active mode. Okay, this you should be very careful about this thing. Okay, I hope this problem is very clear to you. Okay, next we will see something regarding the variation of beta DC with respect to temperature. So variation of beta DC with respect to temperature. Okay, so beta DC is actually, I have told you, it is a constant, but whenever there is a change in the temperature, what you can see is that the beta DC will be changing because of the temperature. Actually, a lot of electrons will be breaking the bond, and it will become free electron, and according to that, actually beta DC will be changing. So how it will be looking like, that's what I am going to draw. Okay, so you have, suppose, the collector current IC in milliampere, and suppose this is 1 milliampere, this is 2 milliampere, like this, and this is 10 milliampere, and let's say this is 20 milliampere, this is 30 milliampere, like this. You have up to 200 milliampere. Okay, 200 milliampere. You can see here that the variation, suppose you have a beta of 10, this is beta DC, you can see here that it will be varying something like this. Okay, at temperature, for example, this is the value of the at temperature, which is equal to minus 55, temperature at the junction as minus 55 degrees Celsius. Okay, if you increase the temperature, you can see the beta DC is changing. Okay, again you have beta DC is changing. So this is at temperature minus 15 degrees Celsius. Okay, and so this is 20 here, let's say this is 30 here, this is 50 here, and 70 here. Okay, so this is how actually it is varying. Now this is at temperature, you can say 25 degrees Celsius, and this is at temperature, let's say this is temperature 75 degrees Celsius. So you can see here that this is a temperature 125 degrees Celsius. Okay, so you can see here that as the temperature increases, you can see the beta DC is also increasing. Okay, beta DC is also increasing. So this is what the variation of the beta DC with respect to the temperature. So beta is not a constant. So that's why we are in transistor circuit. If you have a transistor circuit which is designed for Abaha, if you take this to Riyadh during a hot climate or a hot season, what will happen? There will be a small variation in the beta. According to the variation in beta, you can see a small change in the collector currents also. As the collector current changes, VCE changes. So there are different techniques how to solve this issue by using a clever circuit design. So we have different types of we have seen one kind of biasing. This kind of biasing we will call this as the fixed bias. Okay, this is a biasing technique. That means giving the power supply. So in this biasing technique, you need a power supply here and you need a power supply here. So there is two power supply 1 and 2. Okay, there are two power supply. Okay, so instead of this, we have different configuration of circuit in order to achieve a particular IC and particular VCE. So we have to fix a particular IC and VCE for the transistor. That is the main objective, and this can be provided by using different biasing circuits. Next is the maximum ratings of the transistor. So maximum ratings. Okay, you have the maximum ratings. So like other devices like the diodes and all, BJT is having some limitations. Okay, BJT is having some limitation. So what are those limitations? BJT is having some limitation. That means VCE and IC must not exceed the maximum power dissipation. Okay, maximum power dissipation. If you give some higher voltage or current across VJT, if it cannot withstand it, or it is coming beyond its maximum ratings, then what will happen? It will damage. If VCE is maximum, if VCE is maximum, then the IC can be calculated as that is IC is equal to the maximum power dissipation divided by VCE. That means you know the current power is equal to voltage into current. So using that relation. Okay, so this is how we can calculate the maximum IC. Okay, now we will see a problem based on this. A transistor is to be operated with VCE which is equal to 6 volt. So there is a transistor which is operating at VCE is equal to 6 volt. If the maximum power rating is 250 milliwatts, what is the most collector current that it can handle? Okay, so what is the most collector current? So it is given that a transistor is operating at VCE as 6 volt and the power rating, that is the maximum power rating, okay, or maximum power rating, PD max you can say, is given as 250 milliwatts. Then how much current you can pass through the transistor? So you have to design the value of RC such that it should not exceed this limit. So what should be IC? IC is PD max divided by VCE, which is equal to 250 milliwatts divided by 6 volts. You will get it as 41.7 milliampere. Okay, so if the current exceeds this limit, what will happen? Then the transistor will damage. So this is the maximum limit for the IC. Okay, I hope this part is clear to you. Okay, so next actually we will see how the transistor can act as a amplifier. How the transistor act as an amplifier. Okay, So you have seen the transistor circuit like this. You have RC, you have VCC, and you have RB, and you have VBB. Okay, so this is a particular way of giving the power supply to the transistor to fix IC and IB. So we need to fix first IC and IB, fix IC and VCE, sorry. So how to fix IC? By fixing IB. And how to fix IB? By fixing RB. Okay, so you have to properly select a RB. So before that, I will write the transistor equation anyway. So you know what is the equation for RB, sorry, equation for IB here, and you have seen what is, this is IB, and this is VCE, and the current, this is IC. So what is IB here? We have already seen IB is equal to VBB minus 0.7, because this voltage is 0.7. We have already seen this equation, divided by RB. And what is IC? IC is equal to beta DC times IB. So if you want to fix the IB, if you change the RB, what will happen? IB will change. If you change the IB, IC will change. So how you can fix IC? You can fix IC by fixing RB, not RC. That's very, very important. So you can fix IB by fixing RB. Okay, so you can select any value, whatever it is required for you. Okay, in active mode. So we are talking about in active mode. Active mode. So our amplifier will be working in active mode. Okay, the amplifier will be working in active mode. So in active mode, you can fix IC by fixing RB. Now we have to fix VCE also. So we will take another loop here. This is loop 2. Okay, so this loop, actually I will write the Kirchhoff law. So you will get the VCE as VCC minus IC into RC. Okay, so you have already fixed IC. So how you can fix the value of VCE? You can fix the value of VCE by changing RC. So VCE can be fixed by changing RC. So you have seen that this is an equation of the straight line. Okay, and also we have seen this is the load line. In the last lecture, I have already explained to you. Now we will see what is the transistor characteristics and how we can work it, how the transistor will work as an amplifier. So the transistor characteristics will be like this. Okay, this is x-axis is VCE. So for different values of IB, let's say this is IB0, this is IB1, you will get different values for the collector current. Okay, this collector current is IC0, IC1, and what is this? It is nothing but beta DC times IB1. This is beta DC times IB0. So that's how you are getting. So similarly, you will have different characteristics curve here. This is the complete region for the transistor. And I have already told you this equation is showing you the equation of a straight line. So VCE is equal to VCC minus ICRC. So I will select a point on the x-axis. So what is x-axis? X-axis is VCE and y-axis is IC. So at x-axis, IC equal to 0. So x-axis means IC is equal to 0. If IC is equal to 0, then what is VCE? VCE will be equal to VCC. Okay, when IC is equal to 0, you will get VCE is equal to VCC. So you will get some point here, VCC. Similarly, on the y-axis, in y-axis, you know this is y-axis. On y-axis, we have VCE is equal to 0 because this is the point 0, 0. Okay, so VCE equal to 0. If VCE is equal to 0, then what will be IC? IC is equal to VCC divided by RC, you can use this equation for both of them, okay, using this equation. So this you will get some maximum current VCC divided by RC. Now you can draw a line which is known as the load line. Okay, this is the load line. Okay, this is the load line, and this is the characteristics curve for the complete circuit. So the circuit, since you have a lot of region for the transistor operation, but the transistor will be following only this curve, okay, as shown here. It will be selecting only the points only on this curve. So because this is the intersection, so it is intersecting with many parts of the curve. You can see here it is intersecting here, here, the complete point, okay. So it is intersecting everywhere. Now what I want to tell, this is the load line, this is the load line, okay. Now listen carefully what I am going to do. Sorry, this is my biasing VBB, okay, and I am going to connect sorry, not here, I am going to connect here my source, okay. So this is going to the ground. So this is my V in, okay, this is my input signal V in, okay, V in, and this is my input, okay, V in, and this is the coupling capacitor, I have already told you, okay. Now I can take my output from here as shown here, okay. Now what we are going to see, you can see here, if I don't give any input, my voltage is VCE. So this voltage I will call as VCEQ and ICQ. So you can see here my VCEQ I will be usually fixing somewhere here, okay. How to find this VCEQ? By using the normal equation, this equation, okay, VCEQ, and I can get my ICQ. How to fix ICQ? By using this equation. So to fix IC, I told you, you have to fix the value of RB. So you have to select a proper value of RB so that you will be getting a point at the center, okay. So this is ICQ, and this point we will call it as the Q point, okay. We will call it as the Q point, okay. I hope that is clear to you. So we will call it as the Q point. Now how we can visualize the working of a transistor? Now you can see from the picture that you have a current IB and there is an input. This input will be also giving you something, a small current, which is IB. So the total current the total current at the base is nothing but, you have capital IB which is due to the DC plus small IB which is due to the AC. So this is due to the DC and due to the AC. So what will happen? You will be having a same thing. This is at the base. You will be having a total current at the collector also, because at the collector you will be getting IC due to the DC, and you will get an IC, this is due to the AC. But you know that this will be a large current, it will be very large because it is beta times larger, right? Because IC is equal to beta times IB, okay. So you will be getting a large change in the current. So you will be getting a change in the VCE. So VCE total now, total now will be, VCE will be equal to VCC minus, what is where IC? IC is different now, IC plus small IC, okay, into RC. So if you can see here two parameters, VCC minus IC into RC, this is nothing but your DC part, then minus small IC into RC. So you have an AC part also. So whenever you give an input which is an AC signal, you will get a AC IC current here, and you will get a AC voltage also. So you are getting, and this is very large when compared to IB, because when compared to IB, because IB was very small, but you are getting a large voltage at the output. It is because of the factor beta. Okay, this is the property of the transistor. So the transistor will amplify the signal many times. So even though if you are giving a small voltage at the input, you are giving a small voltage, it will be converted into a large voltage at the output. So this is what happening in the transistor. Okay, so basically you are getting a very large voltage at the output. Now we will see how we can visualize this. Okay, so you are now at a point, actually basically how it will be looking like. You can see here you have a suppose if you measure the voltage at the collector VCE. So if you measure the voltage at the collector, this is the time instant, and if you measure the voltage at the collector, that means VCE, which is equal to VC equal to VCE. Okay, so your voltage was basically, it was VCEQ, but you see here it has been changed by a factor, which is, it has been changed by a number minus IC into RC. Okay, so if you have a large RC, then it will be again amplified anyway. So you can see here it is minus. So if IC increases, so you see here that the AC at the output, the AC current or the voltage at the output is minus IC into RC. Okay, there is a minus sign. That means if IC increases, your VCE decreases. So this is we will call this as small letter VCE. Okay, for AC. Now if IC increases, VCE decreases. So if you have a input like positive and negative for IB, then what will happen? Your voltage will be decreasing as a big number. You will be getting like this, a big voltage. Okay, and this is the change you can see here. Okay, so you are giving a small input, and you are getting a large output. But you can see here your output contains, your VCE contains both. It contains the DC parameter, it contains the DC, this is the DC part, and you have the AC part. Okay, so you have AC and DC in the output. But when you use a capacitor here, what will happen? You will be getting only AC at the output, because the capacitor will block all the DCs. Okay, so the function of the capacitor is to block the DC. So at this point you are getting DC plus AC. Okay, at this point you are getting DC plus AC, but at this point you have only AC. Okay, at this point you have DC and AC, and at this point also you have DC and AC, but at the output you have only AC. That's a very interesting thing, because you have a capacitor. Okay, so we will see how it is working with this picture. Okay, with how it is working, we will show it with this picture. You can see here that whenever you have a input which is varying, then the collector current, suppose you have a small input for the base current, this is IB2, this is IB3. So I will show with the base current variation. Yes, you have it, you have transistor characteristics like this. Okay, now I told you there is load line. The load line, you have VCC and this maximum current VCC by RC. Now you have the Q point, you have to select a Q point, and this Q point is nothing but ICQ, and this is VCEQ. How to fix this? You can fix this by using RB and RC. That means RB is used to fix IC and RC is used to fix VCE. So this is VCEQ. Okay, now I will draw the time axis. So this is the time axis. Okay, you are giving some IB here, so I will show you. You are giving some IB here. This is your IB. Okay, this is your IB. So according to that, you have a variation, something like here it is projecting here, so you have some variation for the collector current. So this is the variation for the collector current. So your IC is varying like this, IP, and you have IC. According to that, you have a variation in the VCE. Okay, so this is the variation in the VCE. Okay, VCE. So this is how it is working. So you have a small variation in the IB, and this IB will be of the order of microampere, but you can see you have, according to that, you have a variation in the IC, but this IC will be having variation in the order of milliampere usually, and you will be having a variation in the VCE. So the VCE also will be varying. Okay, so I can show it here, VCE. Okay, you can see VCE will be like this. Okay, it is because you can see here, whenever the IB is positive, IC is also positive, but VCE is negative, it is going back. You can see it is because you know that VCE is equal to VCC minus IC into RC. There is a minus sign here, that's why. Okay, so that's why we have we are getting actually minus here. Now when the IB is negative, you are getting IC negative, but VCE is positive. So there is 180 degree out of phase, so you, between the input and the output. So VCE is 180 degree out of phase. Okay, so you can imagine the working of the transistor like this. You have a water tank. You can imagine the working of the transistor like this. You have a water tank which is at a huge height, let's say H, and this is the ground. Okay, and you have the valve here, and this is your output. So you have the emitter here which is emitting the water, which huge, and your pipe, your valve is opened half, you can say opened half. Okay, opened half means you are selecting the Q point at the center, that's what the meaning. So you have opened half, so you will be getting some water supply, and you are observing here, and you are this is the collector. Okay, you are collecting the water. Now you are giving a small input here. By using this input, you are giving a small input. Suppose this input is positive, you close the pipe, and if this input is negative, you open the pipe. This is what you are doing. So whenever the input is positive, you close the pipe. Okay, you close, not pipe, yes, you are closing the pipe anyway. This is a pipe or a valve, you can say. So you are closing the pipe. So what will happen? The water will reduce. Okay, water flow reduce. But you know that this the flow of water is usually, it's very high, because you have kept the tank at a large height. This is a large height. Okay, it's huge height anyway. H is very large. So what you can say is that even though you need a small force, this small force you are applying a small force here, you are getting a large force at the output, this water flow. So you are getting a large force at the output. Okay, so whenever you are getting, you have a positive signal, you close the tap, and what will happen? You are getting water flow which is reduced. That means the output is going down, minus. Okay, and it is with a large force, that's why it is amplified. Now when you have a negative, I told you, you are opening the tap. So whenever you have a negative, you are opening the tap. Okay, then if you open, then what will happen? The water flow will increase. Then the water flow will increase. Okay, water flow will increase. So when the water flow increases, you are getting a positive signal. But you know that since the water is coming from a large height, the pressure will be more. So if you use a small force here, you are getting a large force at the output or large pressure at the output. So you can view all of this together as this. You can consider this as your base. Okay, so at the base you are giving the input, so you give input at the base. Okay, at the base. So by controlling the base current, actually you are controlling the output. So this is how it is working. I hope this example is clear to you. So that is how the transistor is working as an amplifier. Now we will see how the transistor will work as a switch, transistor switch. I told you when one problem that if you put a transistor, if you use a transistor as a switch, it has only two modes of operation. One is the active mode and one is the cutoff mode. Okay, so you can basically control the transistor operation. For example, here you have a transistor which is RC, and this is your VCE, VCC, like this, and this is your VBB. Okay. Okay. Now you take the output from here, V out. Okay. Okay, you will take the output not from here. Let's say you take the output from here. This is V out. Okay. Now I told you we will bias the transistor in such a way that it will move to saturation easily. Okay. So let us assume that you have a switch here, a mechanical switch, that's what I am saying. Okay. And now suppose the switch is closed. Suppose this is switch S1. Suppose if S1 is closed, what will happen? If S1 is closed, then what will happen? You will be having a current, you have a base current, and you have a collector current, and the transistor moves to saturation. We will be designing the value of RC. We will design the value of RB and RC such that the transistor moves to saturation easily. Okay, like the problem that we have discussed before. In that problem, you have seen that the transistor easily moves to the saturation. So when the switch is closed, the transistor will move to the saturation. So I will just show you when the switch is closed with red color. This is closed. When the switch is closed, the transistor will move to the saturation. So the voltage VCE sat will be equal to 0.2 volt. So the output V out you are taking from here, it is the voltage between this collector and the ground is connected to the emitter. So V out is nothing but VCE, and at saturation means the switch is closed, switch S1 is closed. Okay, when the switch is closed, what will happen? This become VCE sat, that is nothing but 0.2 volt. Now in cutoff, what is the situation? That means you are opening the switch. Cutoff means I will show with the green color. So you open the switch. Okay. When you open the switch S1. So IB will be equal to 0. So IC is equal to 0. So the voltage drop across the resistance here, the voltage drop across this resistance will be equal to 0, right? If this is equal to 0, this is VRC is equal to 0. So V out will be nothing but VCC. So you will be getting VCC at the output. So we will see a problem with this. Okay, so we will see a problem. You have a transistor circuit like this, and this is RB. The values are same, 10 kilo ohm, and this is VBB, and this is 3 volt. Okay, the values are same as that of the previous problem. RC is equal to 1 kilo ohm, and VCC is equal to 10 volt. Now we will take the output from here, okay, and we have a switch here. Okay, this is the switch S. Now we will see what will be the voltage when this, and also it is given that VCE sat is equal to 0.2 volt. Now when S1, we will see the first condition. When S1 is closed, when you close S1, what is IB? When you close S1, the transistor is biased. I told you this circuit was biased for saturation, because we have already discussed and seen that this circuit, when S1 is closed, the transistor is usually known as Q will move to saturation. It is already given, okay, given that when the switch is closed, the transistor moves to saturation. So when the switch is closed, the transistor moves to saturation, and V out will be VCE. This is the voltage between the collector and the emitter. So VCE, but the transistor, when the switch is closed, the transistor moves to the saturation. So V out will be VCE sat. At saturation, the voltage will be 0.2 volt, because both the end will be forward bias. Both emitter base junction and collector base junction become forward bias because of this voltage configuration. Now, because of the circuit configuration. Now, when the switch, when S1 is opened, IB equal to 0, IC equal to 0, right? Now, what is the voltage across RC? Voltage across RC is IC into RC, but IC is equal to 0 ampere, so VRC is equal to 0. So whatever you have 10 volt here, it will appear across the V out, because the voltage at this point is 0 volt, because when the switch is opened, when the switch S1 is opened, so we will get VCC as the V out. So V out will be equal to 10 volt. Okay, so you have two conditions now. When the switch is opened, you have V out is equal to VCC. That means you have a power supply. Now when the switch is closed, you have V out as 0.2 volt, or approximately 0 volt, you can say. So this is the case, you have no power supply. So you can consider this as a, you can also view the transistor switch as a NOT gate. You might have studied about NOT gate. What is this? You have a NOT gate like this. In NOT gate, if you give 1, you will get 0. If you give 0, you will get 1. That means the switch is opened. Opened means you are giving input 0, and you have a power supply. That means output is 1, logic 1. Now the switch is closed means you are giving a power supply. That means you are giving 1, and at the output you are getting 0. So this 1 means the switch is closed, and you are getting 0 means output is 0. That is, the output is 0. Okay, Now here the switch is opened and the output is maximum. That means the output is 1. Okay, logic 1. So these are all logic anyway, logics. Okay, these are all logic 1. So logic 0 means 0 volt, you can say, or 0.2 volt. And logic, there is also another logic, negative logic, that we are not going to discuss now. So logic 1 means basically usually it is you can have VCC or some voltage. Okay, so you can use this circuit. That means this circuit is also a NOT gate. This is also a NOT gate. Okay, you can also use it as a NOT gate, but it is not a good NOT gate. There are advanced circuits available. Okay, I hope this is clear to you. So